Right. Okay. So let's all right. I saw on Campus Wire and then I got questions during office hours. So I just want to clarify a couple of things, okay? So because I know in my slides from Wednesday, you know, I think I should have deleted the vertical label on some of the plots and to kind of improve things. But anyway, the likelihood function of a binomial probability is not the beta distribution. Okay, so that's important to note. Okay, the likelihood of a binomial probability for n observations with z successes is this. You know, that's the binomial probability, and you treat n and z as fixed values, and it's a function of theta. Okay, so the likelihood function is a function of theta. The n and the z are fixed, and only the theta changes. Okay, you can use R's d binom calculator if you wanted to get this likelihood, and where z and n are going to be fixed values, and theta is the variable that can range from 0 to 1. Okay, so that's important. All right, and also yes, make sure you keep theta on the range or on the kind of domain from 0 to 1. Okay, the likelihood function of a binomial probability for n observations with z successes is going to be proportional to, but not equal to, a beta distribution or a beta distribution PDF, I should say beta PDF with alpha equal to z plus 1 and beta equal to n minus z plus 1. Okay, so it will be proportional to this. This is different because it's not exactly that, because the binomial has this constant in the front, whereas the beta has that beta function, beta alpha beta, with made up all those gamma functions in the front. Okay, and so that's different. Okay, but it will be proportional too. Okay, so the density function of a beta distribution, the PDF here, will integrate to 1, whereas the likelihood functions do not integrate to 1. So that's an important thing to note. With the likelihood function, they don't integrate to 1, whereas density functions do. Okay, so I realize I should have explained this, and maybe I'll go back and edit Wednesday's lecture just to kind of clarify a few things. When I plotted the likelihood function, I did use a beta distribution. I kind of cheated there, and I did plot a beta distribution because it is proportional to the likelihood function. Okay, and it would kind of amplify the shape of the likelihood function. But and the reason for that is because if I did plot the true likelihood function, okay, the density would kind of have a peak up here, and then the likelihood function, which is proportional to, is just going to kind of get squashed down, if that makes sense. Okay, so the likelihood function has a much lower peak than the density function, the PDF, and so if I plotted them at the same kind of thing, the likelihood function would appear very flat, and it's kind of hard to picture what's going on. And so I guess I took some artistic license, and I chose to plot something that was proportional to the likelihood function, but it's technically but it's not the likelihood function. Okay, and so and one thing about likelihood functions is that the more data you have, like the larger this n becomes, okay, this likelihood function will get more and more and more flat. Okay, so as n gets bigger, basically you're going to be taking a power that's less than 1 raised to a bigger number. Okay, and so it's going to get closer and closer to 0, basically. And so more data means your likelihood function gets smaller and smaller and smaller. Okay, and it kind of makes sense because the likelihood function is basically the probability of the data. And the more data you have, it becomes less and less likely to get that specific set of data. Okay, so that's what a likelihood function represents is what is the probability of getting this specific observed data, and so the more data you collect, the probability of getting that specific set of data gets smaller and smaller and smaller. And so so anyway, when you do plot, if you do plot the true likelihood versus a probability density, the probability density will have a peak like this, and then the true likelihood will appear like almost flat if it's a big data set. Okay, if it's a small data set, there might be like a little bump, but it's certainly not going to have a area equal to 1. Okay, does that kind of make sense? Does that help or clarify things? Okay, so if you were asking questions and if you had questions about the homework, don't use d beta for the likelihood of a binomial probability. Okay, you can use d binom. This is allowed, all right, but don't use d beta. D beta is proportional to, if d beta with these properties is proportional to d binom, but it's not the same. Okay, all right. With that out of the way, we're going to get into Bayesian inference, just some basics of this. Okay. All right. So this is what we established earlier this week. We said the beta distribution, the beta probability distribution, is the conjugate prior distribution for data that comes from kind of with a binomial likelihood. And so we're going to say the observed data comes from binomial distribution. And in our observed data, there are a total of n trials and z successes. And the probability of success for each trial is theta. And therefore, the likelihood is equal to this. Okay, the likelihood, I guess, of one particular sequence. I mean, I could put in a constant here, kind of that binomial coefficient in the front. Doesn't really matter. Okay. The prior distribution of the parameter theta is going to be a beta distribution with parameters alpha and beta, and that is given by this function. Okay, so it's 1 over beta alpha beta, and then theta raised to the alpha minus 1, and 1 minus theta raised to the beta minus 1. And then when you multiply the likelihood times the prior, you're going to basically combine the numerators, or not numerators, exponents of this part with this part. And so you're going to get theta of z plus alpha minus 1 times 1 minus theta raised to the n minus z plus beta minus 1. Okay. And then in order to kind of keep it as a PDF, you have to adjust the normalizing constant to make sure that it still integrates to 1. And this becomes the normalizing constant that you would adjust to. It becomes this. Basically, whatever theta is raised to, this is z alpha minus 1. You're gonna becomes z plus alpha right here, and then whatever this is raised to, you basically add 1 to it, and you get this function. Okay, so this, I think this is what we spent all of Wednesday kind of going over, and we established this on Wednesday, so I'm hoping this is okay so far. All right, so far so good. All right, let me go ahead and give you your first quiz answer. It's going to be B as in bear. First quiz answer is B. B as in bear for today's viewing quiz.
Professor, could I ask you a quick question?
Yes, go ahead.
For the likelihood here, there's not the n choose z as there was on the previous page. Is there a reason for that?
I guess I just left it off. This, I guess, so technically, I should have said, this would be a sequence of Bernoullis, which is proportional to a binomial. So I guess I can include the n choose z, but it's not critical, okay? Because basically you just have to evaluate the numerator across all possible values of theta in order to get kind of the denominator. And depending on how you've written your likelihood function, whether you include a constant or not, that's going to adjust basically what that denominator evaluates to, and it'll cancel out. So, so whether you put in a constant here, when you do the multiplication, whatever constant here is going to get multiplied by, this constant over here, and then it all kind of melts away when you kind of just reevaluate this part and find the normalizing constant to make sure that this whole thing, that this whole thing integrates to 1. Okay, so whether there's a constant here or not, this is really the part that I guess depends on theta. And in order to make sure that the entire function integrates to 1, this has to be the normalizing constant. Okay, so here are some proofs, I guess, for properties of the beta distribution. So one thing is that the gamma function, so you're going to see a bunch of gamma functions, but you can, again, the gamma function is a scary thing, but it feels scary, but it's just a factorial, right? Okay, I don't think anybody's afraid of factorial, right? It's just, 5 factorials, 5 times 4 times 3 times 2 times 1. And gamma of 6 is equal to 5 factorial, okay? So it's offset by 1. So gamma of x plus 1 is equal to x factorial, all right? So anyway, the mean is going to be evaluated like this. So the expected value of theta is going to be theta times the PDF d theta, right? So the mean, you do the integral of theta, or x times the PDF, and so it's theta times the PDF of theta, and this is a constant, so I'm going to go ahead and factor that out. And now theta times theta raised to the alpha minus 1. Okay, I realize I can just write theta raised to the alpha, but I'm going to choose to write it this way: theta raised to the alpha plus 1 minus 1. Okay, and then and so this part, when you evaluate it from 0 to 1, is going to be equal to beta of alpha plus 1 comma beta. Is that all right? The jump from here to here. This is kind of just the whenever you have this, the normalizing constant for whatever this is defined as this, and this is kind of the definition of the beta function there. And then the other definition of the beta function is that the beta function of alpha plus 1 comma beta is going to be gamma alpha plus 1 times gamma beta, and then divided by gamma of the sum of these things. Similarly, here I've got 1 over beta, so in the, it's going to be flipped, and so I'm going to have gamma alpha plus beta divided by gamma of alpha times gamma of beta. Okay, and so here I kind of just rearrange a bunch of these terms. So I combine gamma alpha plus beta is this, and then gamma of alpha plus 1, okay, because this is equal to x factorial, or in this case alpha factorial. We can also write this. We can write gamma of x plus 1 is equal to x times gamma of x, if that's okay. All right, and so I'm replacing gamma of alpha plus 1 to alpha gamma alpha. This stays gamma beta, okay? This is gamma alpha, gamma beta, that stays right there. And then likewise down here, gamma of alpha plus beta plus 1 is going to equal alpha plus beta times gamma of alpha plus beta. I hope this slide's okay. All right, and then so you cancel out a whole bunch of terms. So basically this cancels out with this, these cancel out with this, and you're going to be left with alpha divided by alpha plus beta. All right, and so that's going to be the mean of the beta distribution. All right, and that aligns with like if we go over to beta distribution on Wikipedia, the mean is alpha over alpha plus beta. Okay, so so if you match Wikipedia, it's a good sign, right? Generally speaking. Okay, is that good? All right, and then the mode, to solve the mode, that's kind of the maximum of the beta distribution. That's going to be equal to alpha minus 1 divided by alpha plus beta minus 2. And then the way we solve for the mode, or the maximum, this occurs where the derivative is 0. Okay, so this is going to happen where the derivative is 0. So I'm going to take the PDF of the beta distribution. I'm going to take the derivative of this. Okay, and so this thing is just a constant. I'm going to take the derivative with respect to theta. This is just a constant. And then so this is a product. So you've got kind of basically the derivative of the first times the second plus the second part, second factor times the, what did I say? Derivative of the first times the second plus derivative of the second times the first. Okay, so anyway, derivative of the first becomes alpha minus 1 times theta raised to the alpha minus 2 multiplied by that. And then the second part, you take this, theta to the alpha minus 1, and you multiply by the derivative of this, which is going to be beta minus 2, 1 minus theta times beta minus 2. And because there's a negative in here, you know, via chain rule, you have negative 1. Okay. And then so if you kind of rearrange, this is all just rearranging algebra terms here. This becomes, you can factor out of all of this. So I just deleted this, or not deleted, I got rid of it because over here is 0. So I can just ignore this constant. And out of this, you can factor out a theta to the alpha minus 2 and a 1 minus theta to the beta minus 2. And the remaining terms is going to be this, all right? So, so technically, the derivative is also 0 when theta equals 0 and theta equals 1. Okay, so at theta equals 0 and theta equals 1, the derivative is also 0. But basically, we're just trying to solve for where theta could equal 0. And then so anyway, I'm going to delete this also, and we're just going to focus on this part. And we have basically this. We've got alpha minus 1, 1 minus times 1 minus theta times beta minus 1. And if you kind of multiply everything out, you're going to get this. Alpha minus 1 minus alpha theta plus theta. And then this becomes theta beta plus theta. And then if you factor out a theta, so over here, there's no theta term. So you get alpha minus 1 minus, and then you have theta times alpha plus beta minus 2. This thing is equal to 0. So you just bring this to the other side. And then you divide both sides by alpha plus beta minus 2. And you're going to get a maximum occurs, or you're going to have the derivative equal, where theta is equal to alpha minus 1 divided by alpha plus beta minus 2. Okay, wait. All right. So I got a question. It says, can you explain how you went from the step of theta equals, wait, which step? Is it on this slide here?
Yes. So over here where you've written the derivative is also 0 when theta equals to 0 and theta equals to 1. Can you explain how you went from that step to the step after that?
So from this step down to this step?
Yeah.
Okay, so basically I just, assuming theta is not 0 and theta is not 1, I just divided both sides. I divided 0 by this quantity and 0 by this quantity.
Oh, okay. That was
Okay.
pretty simple. Okay, thanks.
So I just, so yeah, assuming that theta, so theta equals 0 is a solution to this, and theta equals 1 is a solution to this, because these would become 0. And then so assuming that theta is not 0 or 1, these are going to be some constant, or not some constant, but some kind of value here. And I can divide both sides by that. And we're going to get 0 equal to just basically this portion of the product.
Thank you.
Yeah. Okay, so that's the mode of the beta distribution. So this will come in handy in a later slide here. All right. with Bayesian statistics, we can make probability intervals. And these are basically the Bayesian version or alternative to a confidence interval. So in frequentist statistics, we say the unknown parameter is fixed, and so we can't talk about the probability that the parameter falls within some certain bounds. It either is in the bound or it's not in the bound, but there's no probability of whether the unknown parameter falls within the chosen bounds. Okay. In Bayesian statistics, the unknown parameter is a random value. So we can say that there is, like a 95% probability that the parameter does fall inside whatever chosen bounds we've done. Okay. And so there's a few popular methods for determining the bounds of the interval. And two methods I'm going to look at is the equal tail credibility interval and then the highest posterior density interval. All right, and so as far as the equal tail interval goes, is that you're going to try to make sure that the probability of being above the credibility interval is equal to the probability of being in the area below the credibility interval. Okay, and so if the posterior density is known, then you can kind of use the quantile function. Okay, so I'm just making this up. So this is, I guess, a different example. So far, we've always been using kind of beta distributions, but here I'm going to just pretend we've got a gamma distribution. Okay, so let's say the posterior distribution is known to be a gamma distribution with shape parameter 5 and rate parameter 1.5. Okay, and so in R, basically, you're going to use the Q gamma, the quantile function. And for a 95%, you want 2.5% below and 2.5% above. Okay. And so it's going to say the bounds of this are going to be 1.08 and 6.827. So the gamma distribution is this skewed thing, and you would find the bounds using Q gamma. And because we want the middle 95%, we're going to say we want 2.5% below and 97.5% above. All right. And then and when you plot this, it looks like this. Okay. And so I don't know if you guys are familiar with mosaic and the XP functions, but so in R, you have like your P functions like P norm and P whatever. Okay, so here you can have P gamma, but then in with mosaic, you can type in XP, XP whatever distribution, and it will just automatically create a plot for you, which is really nice. You put in some a vector of values, and it's going to just draw cutoff lines here. And so you can see, according to our plot, there's 2.5% probability of being in the purple region, 2.5% probability of being in the green region, and whatever color this is, blue, teal, something, okay? 95% probability of being in this middle region here. All right, so that's the equal tail interval. This area is 2.5% and this area is 2.5%. And I think I have you guys do something like this in your homework, but obviously for, I think, the beta distribution or something. You also have the highest density interval. The highest posterior density interval finds basically the narrowest range where you can still get 95% of the posterior distribution, okay? Because you're picking kind of the area that has the highest probability density, okay, for the posterior distribution. And so one thing about this is that the value of the density function at the lower bound is going to be equal to the value of the density function at the upper bound. Another way you can think of this is that you're taking the density function and you're kind of, you've got like this rising tide of water, and basically where are the, where would the watermarks be drawn? Okay, And that would be kind of the highest posterior density interval, okay? And so you can find it using, there's a package called HD interval that we can use to find the upper and lower bounds. So here again, I'm going to have a gamma distribution, and I've got shape 5 and rate 1.5. And so here, rather than saying I want the 2.5th percentile and 97.5th percentile, I'm going to call in the function HDI. I use I specify the function, the quantile function that I want it to solve for. So I've got Q gamma. We're going to say I want the middle 95%. And again, you can change this if you want to make a 90% credibility interval or 80% credibility interval or something. And then you provide it the shape and rate parameters or whatever parameters are necessary to define this distribution. Okay, and so here it tells me that the bounds are going to be 0.804 and 6.2868. Okay, and so if I plot that, this is the resulting plot here. Okay, and so so the height here at this this location is the same height as over here. Okay, and so if we were to kind of take this probability density curve and kind of dip it in water, it would draw kind of a line here, okay? And so you still have 95% in the middle, but now you have a little bit less than 1% here, 0.008 on this side, and you have something close to 4%, a little over 4% on this side, okay? So if you compare this, here you have 95% in the middle, but you have 2.5% over here and 2.5% over here. That's the equal tail credibility interval. And the highest posterior density interval looks like this. You still have 95% in the middle, but the bounds are different, okay? The bounds have changed. If you've got a symmetric distribution, it's going to be the same. But if you've got a skewed distribution, there will be a difference between the equal tail and the highest density intervals. All right, so, you know, should you choose one over the other? I don't know. I wouldn't say one is more correct or less correct than the other. I think maybe the highest density interval is a little bit more of a popular choice, but it's not wrong, okay? So the equal tail interval is not wrong either, okay? So whether you select the equal tail interval or the highest posterior density interval, it is correct to say that there's a 95% probability that the unknown parameter falls within the bounds of the interval. Okay, that's a correct thing to say. Okay, and so keep in mind that when you say there's a 95% probability that the parameter falls within the bounds of the interval, this probability that we're expressing expresses a subjective belief, right? Because in Bayesian statistics, probability represents a subjective belief about you know, whatever it is. Okay. And so, you know, in Bayesian statistics, and you create a credibility interval, the credibility interval incorporates our prior knowledge in the form of the prior distribution that we used in the calculation of the posterior distribution. So the credibility interval is based on the posterior distribution, but that posterior distribution that we created depends on the prior distribution. So whatever prior information we have is going to get factored into our it ultimately determines our credibility interval. And so and I've tried to illustrate this in your homework problems as well, because I have you create confidence intervals and credibility intervals, is that in cases where you have little observed data, your credibility interval is going to be heavily influenced by your prior beliefs, right? So I think in the first example, you have like 10 hits. So based on just a few observations, your credibility interval for what you believe to be the where the batting average is depends a lot on your prior information. That it's going to look a lot like, you know, pretty much all players have batting averages over 0.2, and less than 0.4 and things like that. And that information structures your credibility interval, okay? But as you gather more and more data, okay, in cases where you have lots of data available, then this credibility interval is going to get influenced more by the data, okay? On the other hand, if you're talking about a frequentist confidence interval, a frequentist confidence interval is determined only by the observed data, okay? And so if I think in your homework, if you get 4 hits out of 10, the frequentist confidence interval is going to be centered at 0.4, okay? With only 10 observations, there's a huge margin of error. It's centered at 0.4, but there's huge margins of error, okay? And then as you gather more and more data, those margins of error shrink. But again, the confidence interval is based entirely on the data only, and you're not factoring in any kind of prior knowledge, okay? And so that's a big difference, or kind of a core and central difference between Bayesian statistics and frequentist statistics. Frequentists will say, let's look only at the data, and Bayesians will say, you know, it doesn't make sense to look only at the data. You know, we know, like we know stuff, you know, and we should be able to factor in our prior knowledge somehow. I don't know, maybe I can show you a comic. Let's see, XKCD Bayesian, frequentist versus Bayesians. Okay, so the question is, did the sun just explode? And the neutrino detector measures whether the sun has gone nova, but then it rolls 2 dice, and if they both come up as a 6, it will lie to us. Otherwise, it tells the truth. Okay, so this is some contrived scenario. Okay, let's try it. Has the sun gone nova? Roll if it says, and it comes back and it says yes. Okay, so the frequentist will say the probability of this result happening by chance is 1 in 36 or 0.027. Since p is less than 5%, I conclude that the sun has exploded. And then the Bayesian says, I bet you 50 bucks it hasn't, right? Because, so the frequentist looks solely at kind of the data that's been given, whereas the Bayesian will kind of factor in kind of our knowledge and prior knowledge. And we know that even prior to any data coming in, the probability that the sun has exploded is very, very, very low. And so this seems unlikely. And so even though there's a very low probability, you know, according to frequentists, it's less than 5% is considered low. You know, even lower is kind of the prior knowledge, or the prior probability that the sun has exploded. Okay, so anyway, so Bayesians factor in kind of outside knowledge other than the data, and that can cause some, I guess, rift or disagreements between Bayesians and frequentists. Okay, anyway, let's keep going. All right, this is just a slide on conjugate priors. We've been exploring the beta and the binomial distributions because those are a pair of conjugate distributions. This is kind of the Wikipedia definition of a conjugate prior. If the posterior distribution, that is the probability of the function for theta given x, ends up being in the same probability distribution family as the prior distribution, p of theta, then we say the prior and posterior are conjugate distributions. And that prior is the conjugate prior for the likelihood function. And so when we have binomial data, it combines very nicely with that beta prior distribution so that the posterior distribution ends up being a beta distribution, okay? And there's a bunch of conjugate priors. And in your homework, I think I give you a few of these things. I think, what did I give you? An exponential and a gamma pair? I think you got, I can't remember. Is it exponential data with a gamma prior distribution? I think that's what I gave you. And then you also have a normal observation with a normal prior distribution as well. So, so this is useful. Oh, let me give you your second quiz answer. Second quiz answer is D as in dog. D as in dog is your second quiz answer. D as in dog is your second quiz answer. All right, okay. What do we do now that we have the posterior distribution? Can we use it to make predictions? Yes, okay. So we go back to our baseball example. We said our prior distribution was this, beta distribution with alpha 81, beta 219. We observed a new player with 10 at-bats, gets 5 hits, and so our posterior distribution for theta, after we observe our data, is now a beta distribution with alpha 86 and beta 224. Okay, so hopefully this is so far so good. Okay, and so the question is, all right, if this player has 3 at-bats at the next game, what's the probability that he gets exactly 2 hits? What's the probability he gets exactly 2 hits? All right, so the answer, right? If this player has 3 at-bats in the next game, what's the probability he gets exactly 2 hits? That answer is going to be 3 choose 2, theta squared, 1 minus theta to the 1. Okay, so this part's okay, right? This is just a binomial probability, 3 at-bats getting 2 hits and 3 at-bats. Okay, but we don't know what theta is, right? Theta is a random variable, so we don't know what theta is. Okay, so how do we answer this question if you don't know what theta is? All right, so there's a few strategies. Okay, one is you could just use a single value. You can use the mean of the posterior distribution. Another is you just use a single value, but you use the mode of the posterior distribution. Okay, so these are okay. And then, but probably more desirable would be you find the expected value, okay? And we can find the expected value of the probability analytically sometimes. And then this is basically the purpose of our course, is that if we can't do this thing the analytic way, then we can also just estimate the expected value of the probability via Monte Carlo, okay? And so, I only got 10 minutes. Okay, so anyway, if you use a single value, use the mean of the posterior distribution. Okay, so we understand things about the beta distribution. The mean of the beta distribution is going to be 86 divided by 86 plus 224. We get something like 0.2774. And basically, I plug this into the probability, this question. If this player has 3 at-bats, what's the probability he gets exactly 2 hits? I plug in this number, and this is the number that I get. All right. Okay. I hope that's okay. All right. Here, we're going to use a single value. Oops. This is the mode of the posterior distribution, not model, but and the mode of the posterior is, it should say alpha minus 1, 86 minus 1 divided by 86 plus 224 minus 2. So we get a number that's ever so slightly different. The mean is 0.2774 and the mode is 0.27597. If I plug that in and I do the calculation, I get a slightly different answer, 0.1654. So I get 0.1668 if I plug in the mean. If I plug in the mode, I get 0.1654. Right? So these are just some options if you're going to just plug in a single value, right? I think we would agree that this is better, that these is a better idea than the frequentist approach. Maybe I should have thrown in the frequentist approach just for contrast. The frequentist approach would have been, 5 hits, 10 at-bats. My estimate for theta is 0.5, right? We're estimating that the batting average is 0.5, and I would be plugging in 0.5 into these numbers. But we know that's like unusually optimistic about the the player's batting average performance, because it's unrealistic for the player to have a batting average of 0.5. All right. Then I think better than plugging in one single value, though, is to find the expected value of the probability. Okay, so we want to find the expected value of this probability, and we're going to basically consider all possible values of theta. Oh, there's a typo here again. Okay, so there is a function known as or not a function, a theorem, law of the unconscious statistician, okay? And it's used to calculate the expected value of a function g of x of a random variable x when you only know the probability distribution of x, but you don't know the actual distribution of g of x, right? So it's kind of just like, what's the like if you might know the distribution of a normal distribution, but then if you apply a function to it, like you raise it to the 4th power, what's the distribution of that function? I don't know, okay? But the expected value is just going to be the expected value of g of x as the integral of g of x times f of x, where this represents kind of the PDF, all right? So in our case, f of x is the PDF of a, sorry, this slide has a bunch of typos. I'm going to have to fix them all, okay? This is the PDF of a beta distribution. That's a typo. PDF of a beta distribution with alpha 86 and B224. And then the function g of x is the answer to our probability. And that's going to be 3 choose 2 theta to the theta squared 1 minus theta to the 1, okay? And so the expected probability of getting 2 hits in 3 at-bats for a player whose batting average is a random variable modeled by the beta distribution with alpha equal to 86 and beta equal to 224 is going to be equal to the expected value of this, okay? 3 choose 2 theta squared 1 minus theta to the 1 multiplied by 1 over beta 86 224 theta raised to the 86 minus 1 1 minus theta to the 224 minus 1. Okay. All right. And so we need to solve this integral here. And that's what this slide is. Okay. So I'm going to take this constant out and I'm going to put it here. And I'm going to take 3 choose 2 evaluates to 3. Okay. So I put that right there. And then so now I've got the integral from 0 to 1 of theta squared 1 minus theta to the 1 theta to the 86 minus 1, 1 minus theta to the 224 minus 1. These combine, theta squared and theta to the 86 minus 1 becomes theta 88 minus 1, and 1 minus theta to the 1, and this combined to 1 minus theta to the 225 minus 1. All right, so now I have this, and kind of using this definition, I can say that this is going to evaluate to beta 88 225. All right, so is this step okay? Going from here to here, right? So this is kind of just the definition of that beta function. Okay, and then using the definition of the beta function, this becomes gamma of 88 times gamma of 225, and this is gamma of 88 plus 225, and then this is on the denominator, so it becomes gamma of 86 plus 224, gamma of 86 times gamma 224. And so I'm going to kind of rearrange some terms, and I get gamma 310. This adds up to 310. These add up to 313. So I've got gamma 310 divided by gamma 313. Here I've got gamma 88 divided by gamma of 86, and then gamma of 225 divided by gamma of 224. So this is just a whole bunch of gamma functions. Oh, and the whole thing is still multiplied by 3. All right, okay, so using kind of the equivalent that gamma is equal to the factorial function, the 310, gamma of 310 is equal to 309 factorial. This is equal to 312 factorial. This is equal to 87 factorial. This is equal to 86 factorial. I mean, sorry, 85 factorial. This is equal to 224 factorial, and this is equal to 223 factorial. And so this thing becomes 1 divided by 310 times 311 times 312. 87 factorial divided by 85 factorial is 87 times 86. And 224 factorial divided by 223 factorial is 224. And so when you compute all of this out, you get 0.16715. All right, is that okay? The analytic approach to getting the expected value of this function of, it was a simple question. What's the probability of getting 2 hits and 3 at-bats, right? Normally a very easy question, you just plug in a number, but now, because theta is a random variable with its own distribution, we have to solve an integral to get the expected value here. Okay, so this was a problem that we were able to answer analytically, but what if you didn't want to have to deal with all of these gamma functions? Okay, what do you do? All right, well, you can also estimate the expected value of the probability via Monte Carlo methods, okay? And so this quantity, so this is something we call Monte Carlo integration, and we'll cover this in a couple of weeks after we talk about some basic Monte Carlo ideas, is that you can just take it as the mean, okay? The mean of applying the function g to some sample of values, right? So we're going to have xj are going to be values randomly drawn from a distribution with this particular PDF, okay? So we're going to draw values from this PDF. And in our case, the PDF, again, sorry, this is the typo I keep, this is a beta distribution. The PDF is a beta distribution with alpha equal to 86 and beta equal to 224. And I can use R's function, R beta, to generate random values from this distribution. All right, and then the function is this. And so I'm going to generate a sample. I'm drawing 1 million values from the beta distribution. Okay, so from the beta distribution, I'm going to draw 1 million values with shape parameters 86 and 224. And then I have this function, which is going to be 3 choose 2 or 3 times theta squared times 1 minus theta to the 1. All right. And so basically, I'm going to just apply this function to all of the values that I've drawn from the beta distribution. So I have g of the sample, and then I ask for the mean of that. And so this is an estimate of the analytic solution. And if you take a look, it's a pretty good estimate. So the analytic solution says the answer is 0.1671515. All right. This required 1 million draws to get an estimate, but I get 0.1671577, right? So this is an estimate of this. And we can say it's a pretty good estimate, right? And if you did only like 10 to the 5th or 10 to the 4, you know, your estimate probably won't be as accurate, but it'll still get you in the ballpark, right? So how accurate do you need your value to be? How computationally expensive is it to get 1 million draws or 100,000 or 10,000 draws? You know, those are going to be values to think about. Okay, so all to say is that, you know, if we compare the Monte Carlo estimate to the analytic answer, it's a pretty good estimate, okay? And later on, you know, you might encounter situations where the math, the analytic approach, is intractable or too hard to solve, right? Like, what if we didn't know this identity, right? Like, if we didn't know that this was equal to this, you know, we'd be in trouble, right? Because just trying to integrate this, I don't know if we can do this, right? Like, are we going to expand this and try to integrate this? Like, that would be completely terrible, right? So how do you integrate this? Like, we're lucky we have this identity, but if we didn't have this, you know, you'd have to what, expand this, you know, raised to the 224. That's ridiculous, right? So it's so sometimes the analytic math is going to be completely intractable or too hard to solve. And so for these types of problems, we're going to use on the Monte Carlo methods to kind of estimate desired quantities. And this is the reason why Monte Carlo methods are frequently used in Bayesian statistics, because the parameter is going to be a random variable, and solving a problem like what's the probability of getting 2 hits and 3 at-bats, solving a problem like this involves an integral because theta is not a single value. It's a random variable with its own distribution, and you have to consider all of these values. And so because of that, we like to use Monte Carlo methods in Bayesian statistics. Okay, that's it for today. I've got some typos to correct in my slides, so expect an updated version of this, and I'll probably have to create an updated version of Wednesday just to kind of get rid of the vertical axis in these graphs, so to avoid any kind of confusion here. Oh, last quiz answer, thank you. Last quiz answer is E. E as an elephant. Last quiz answer is E as an elephant. Okay, that's it. That's it for today. Have a good weekend, you guys. We'll see you Monday.